In this video, we're going to start Chapter 4 of the chemistry textbook. Chapter 4 is on reactions in aqueous solutions. We're going to go through the opening section, which talks about general properties of aqueous solutions. So the previous video was sort of a more detailed overview of what the textbook is intending to do in this section, in this opening section, which is, so before we talk about the three types of reactions we're going to be talking about in aqueous solutions in this section, precipitation, acid, base, and oxidation reduction reactions. The purpose of the opening section is to make sure that we understand what exactly an aqueous solution is. And then furthermore, what an electrolyte is, what a non-electrolyte, a weak electrolyte, and a strong electrolyte is. Because these concepts are necessary to be able to understand and interpret and visualize these reactions that we're going to be studying. Okay, but in my opinion, this opening section could be a bit more detailed to really act as a better primer for the remainder of the chapter. Because really, but before we start talking about these reactions, yes, we want to understand what an aqueous solution is. We want to understand what a non-electrolyte, a weak electrolyte, and a strong electrolyte is. But we also want to understand what the process of dissolving, a substance dissolving in another substance, what exactly does that mean? What does solubility, the solubility of a substance mean? And how exactly is solubility and dissolving related to electrolyte properties, right? When a substance dissolves in another substance, is that a mixture? What kind of mixture is it? Air is a mixture, right, of different gases. It is like mainly nitrogen and oxygen gas. It is like the nitrogen dissolving in the oxygen, or how does that work, right? So that was the main purpose of the previous video. It was sort of an enhanced version of this opening section. But we'll go ahead and read through this section of the textbook here as well. So, okay. Many chemical reactions in virtually all biological processes take place in water. In this chapter, we will discuss three major categories of reactions that occur in aqueous solutions: precipitation reactions, acid-base reactions, and redox reactions. In later chapters, we will study the structural characteristics and properties of water, the so-called universal solvent, and its solutions. Okay, so yeah, the first sentence. Many chemical reactions in virtually all biological processes take place in water. Why are we about to go through an entire chapter where we're strictly going to be studying certain reactions that occur in aqueous solutions, which is meaning in water? Reactions between substances dissolved in water. Why are we going to go through a whole chapter just on reactions taking place in water? Well, because we know that about 70% of the entire Earth is covered in water, and around 50 to 70% of the human body is water. And one of the things that makes water, one of the properties of water that allows it to be so essential to life and just processes, is that it's what's called the universal solvent. Water is able to dissolve more substances than any other liquid, right? So what we're going to be doing in this chapter is looking at the three of the primary types of reactions that occur in water, in nature, in industry, in biological processes. Okay, and again, these reactions are precipitation reactions, acid-base reactions, and redox reactions, or oxidation reduction reactions. Okay, so general properties of aqueous solutions. So first of all, what is an aqueous solution? Well, okay, let's remind ourselves, we learned in Chapter 1 what a solution is. A solution is a homogeneous mixture. So in Chapter 1, we talked about the different ways in which matter is classified. You've got substances, which is just, they have a definite chemical composition, like H2O or oxygen gas, etc. It's just this one chemical, a substance, you can characterize a substance with a single chemical formula, like a molecular formula, right? Or an empirical formula. And substances are going to be either compounds or elemental substances, elemental forms of substances. Okay, now the next category was if you could have two or more substances combined together into like one bulk to make one bulk substance to where each of those substances retains its chemical identity. And that's what's called a mixture. And there were two types of mixtures. There was homogeneous mixtures and heterogeneous mixtures. To where the homogeneous mixtures, the characteristic was that you could think about that they were mixed thoroughly well to the point where it's like a uniform mixing. At every position within the mixture, the concentrations of the different substances mixed in are all the same everywhere. Okay? And so that's not the case with a heterogeneous mixture. So a homogeneous mixture of a homogeneous mixture you can also call a solution. Another name for a homogeneous mixture is a solution. So a solution is a homogeneous mixture of two or more substances. And now for the case of a solution, you can call the different substances involved a solute or solutes and a solvent. You only use the terms solute and solvent for homogeneous mixtures. And the solute is the substance present in the smaller amount, and the solvent is the substance present in the larger amount. So there's only going to be one solvent in a solution, the substance present in the largest amount. But there could be more than one solute, more than one substances present in the smaller amount relative to the solvent. Okay, a solution may be gaseous, such as air, solid, such as an alloy, or liquid, seawater, for example. Yeah, so we talked about in the previous video, there's different types of mixtures. Well, they come in all forms, like a solid in liquid, liquid in liquid, solid in solid, liquid in solid, gas in liquid, right? So like a solution between two gases would be air. It's okay. We also talked about a solution, a homogeneous mixture. The characteristic of a homogeneous mixture that distinguishes it from a heterogeneous mixture is, yes, it's mixed thoroughly well, but it mixes down to the molecular level. Each molecule is mixing. Okay, that's what happens in the dissolving process is at the molecular level, the solute gets broken up and each molecule or ion is surrounded by the solvent molecules. Now, every homogeneous mixture it's not like every single homogeneous mixture is created through dissolving, like air, which is mainly oxygen gas and nitrogen gas. That's not a dissolving process. That's just more of like diffusion, right? Where like something dissolving in water, like sugar dissolving in water, you have the sugar molecules getting broken up, and then they're fully surrounded by water. Each molecule is fully surrounded by water molecules with these bonds, these like polar bonds, chemical, like not full chemical bonds like in a molecule, but it's still like a bonding process. That's dissolving. Okay, but again, it's not like dissolving has to take place to create a homogeneous mixture. As long as it's happening, the mixing is happening at the molecular level, like oxygen gas and nitrogen gas and air, then you consider it a homogeneous mixture, a solution. But any mixture that is created through dissolving is a homogeneous mixture. Okay, but now in this section, we're discussing only aqueous solutions. We're only thinking about a certain type of solution, a certain type of homogeneous mixture called an aqueous solution, in which the solute initially is a liquid or a solid and the solvent is water. So yeah, an aqueous solution is a solution where the solvent is water. That's an aqueous solution. It's if something is in an aqueous environment. So we're going to see in a second, when you write a chemical formula, we can put the different states, right, of each compound, if it's solid, liquid, or gas. If you could also designate aqueous. If something is aqueous, if a substance is aqueous, that means it's dissolved in water. That's what it means, dissolved. So it's not just, aqueous doesn't mean it's a water environment. I could drop a marble into a glass of water, but it doesn't dissolve, and so I don't consider that aqueous. I wouldn't put in a chemical formula that whatever the marble is made of, and then it gets put into H2O, and now it's aqueous. No, it needs to dissolve to be considered aqueous. Okay, we'll talk more about chemical formulas in aqueous in a second. Okay, now it also says here that the solute initially is a liquid or a solid, and the solvent is water. I'm not sure why they say that, because we're going to see an example in a few minutes of a gas dissolving in water and it becomes aqueous. It was like hydrogen chloride gas. It turns into hydrochloric acid. So I'm not sure why they said it this way, but it's really anything dissolved in water that's what's aqueous. Again, it's not just a water environment. It needs to be dissolved in water. Okay, so now we're going to talk about electrolytic properties. We don't talk about solubility properties until the next section with precipitation reactions. But in the previous video, we go through all the properties of related to water, dissolving in water, etc. So, okay, all solutes that dissolve in water fit into one of two categories: electrolytes and non-electrolytes. Yeah, so, and something being an electrolyte or an electrolytic property of something, it doesn't just apply to water. What we're about to read here, you can think about it. If something is an electrolyte, if it dissolves in any substance, like oil can dissolve fats, waxes, etc. But we're focusing on water. So we're thinking about, okay, we have some substance, a potential solute to put into water. If that substance is soluble, so meaning it's going to dissolve to at least a measurable extent. Just because you might have something that it dissolves a tiny amount, but barely any, you consider that still insoluble. So as long as you have a substance, right? And like a marble would be insoluble. Sand is insoluble in water, even though a little bit does dissolve. It's still considered, it's so negligible you consider it insoluble. If you have a substance that is soluble in water, then that substance, one of its properties is you can say, okay, it's either going to be an electrolyte or a non-electrolyte. And really, if a substance is insoluble, then that's also a non-electrolyte as well. And you'll see what I mean in a second. So an electrolyte is a substance that when it dissolves, results in a solution that can conduct electricity. A non-electrolyte does not conduct electricity when dissolved in water. And so based on this definition of non-electrolyte, if you have an insoluble substance, well, then it doesn't even dissolve, so it's not going to conduct an electricity in that sense either, so it's technically a non-electrolyte as well. Okay, but so, all right, the figure below shows an easy and straightforward method of distinguishing between electrolytes and non-electrolytes. A pair of inert electrodes, copper or platinum, is immersed in a beaker of water. To light the bulb, electric current must flow from one electrode to the other, thus completing the circuit. Pure water is a very poor conductor of electricity. However, if we add a small amount of sodium chloride, the bulb will glow as soon as the salt dissolves in the water. Solid NaCl, an ionic compound, breaks up into Na plus and Cl minus ions when it dissolves in water. The Na plus ions are attracted to the negative electrode and the Cl minus ions to the positive electrode. This movement sets up an electric current that is equivalent to the flow of electrons going along a metal wire. Because the NaCl solution conducts electricity, we say that NaCl is an electrolyte. Pure water contains very few ions, so it cannot conduct electricity. So, okay, what makes a substance an electrolyte, we just saw the definition of an electrolyte is that when it dissolves in water, the water can conduct electricity in the sense that if we come here, they have this pair of inert electrodes, copper and platinum, dipped into the water, they're separated, and there's an electric potential across them because it's connected to a battery, right? And the idea is if it's just pure water can't conduct electricity. But if you dissolve an electrolyte into the water, then all of a sudden the light bulb lights up because there's an electric current going between the two electrodes. That's the idea of an electrolyte. Now, but how is this happening? What they're saying is that if you have something, it needs to dissolve in water. Some solute's going to dissolve in water, and when it dissolves, the result is ions dissolved in the solution. So, for example, they give the example of sodium chloride. Well, any ionic compound that is soluble, you could have ionic compounds that aren't soluble. If you have a soluble ionic compound, then it's going to break up into ions. It's going to get you're going to have these ions, like you're going to have the sodium cation and then the chloride anion, just completely surrounded by water molecules. You'll have the oxygen ends of the water molecules surrounding the sodium cation, and then you'll have the hydrogen ends of the water molecule bonding with the chloride anion. You have these hydrated ions in solution. And what they're saying is that with the electric potential applied, the positive ions migrate towards the negative electrode, and the negative ions migrate towards the positive electrode. And that's how the circuit is created. So again, if you have any substance that when it dissolves in water, it yields ions, you have to have a substance that has to be soluble. So just because you could have an insoluble substance, that like an ionic compound, but even at a very small extent, it's considered insoluble. It's still dissolving. So it is dissolving into ions, if it's like an ionic compound, for example. But it's yielding so little ions that it's not going to conduct electricity, the solution, right? So it needs to be soluble, and then it also needs to be the type of soluble to where it yields ions. Then you have an electrolyte. Like, for example, sugar, right? Sugar is fully soluble in water, right? But each sugar molecule breaks up and gets hydrated. But sugar molecules are neutral. In a solution, a sugar water solution, it's just each sugar molecule is fully hydrated. But again, a sugar molecule is a neutral molecule. It's not an ion. So sugar is a non-electrolyte. It's not yielding. It's soluble, but it's not yielding any ions in solution. So it's really you need to be an electrolyte. You need to be soluble in water. But also, you need to yield ions whenever you dissociate during the dissolving process. Okay, now, comparing the light bulb's brightness for the same molar amounts of dissolved substances helps us distinguish between strong and weak electrolytes. A characteristic of strong electrolytes is that the solute is assumed to be 100% dissociated into ions in solution. By dissociation, we mean the breaking up of the compound into cations and anions. Okay. So what they're saying is that for this demonstration here, you've got the same amount of water, and then you've got these electrodes, and it's the same chemical potential across the electrodes, and then they're dissolving equivalent molar amounts, so the same number of molecules, or at least like if it's an ionic compound, the same number of units of the ionic compound, into each beaker. But like this is going to be a non-electrolyte, this is going to be what they're calling a weak electrolyte, and this is going to be what they're calling a strong electrolyte. And they're saying that a strong electrolyte, what makes something a strong electrolyte is that it's going to 100%, it's assumed to be 100% dissociated into ions in solution. Okay, so what that means is, for the case of sodium chloride, and what we're going to see, all ionic compounds that are soluble are going to be strong electrolytes. So you've got for any ionic compound, it starts off solid, that is soluble. You put it in water, then it breaks up into ions. And each of the ions gets dissolved. So each of the ions are considered aqueous. The environment of the ion is aqueous. You have a positive ion that's completely surrounded and bonded with the more weaker chemical bonds, the polar bonds, but still bonded to water molecules on the oxygen end, right? It's aqueous. It's dissolved. It's in an aqueous environment. The sodium cation, the same idea with the chloride anion. That's why you put the state of it as aqueous. It starts off as solid, like in a beaker. You could just take some salt out, right? Like a teaspoon of salt, right? It's just solid. Then you put it in water and mix it in. The state changes. It's not solid, liquid, or gas. You call it aqueous. It's dissolved, right? If you have an insoluble ionic compound and you put it in water and it doesn't dissolve, it just stays clumped together, or just these little pieces, right? It's in a water environment, but it's not dissolved, so you would still just call that solid. So like silver chloride, for example, is an insoluble ionic compound. So if you put it into water, then the result is just silver chloride, solid. Nothing happens. Yes, this is in a water environment now in a certain sense, but it's not dissolved, so you don't put aqueous. Okay, but it's a strong electrolyte, and you indicate that by this arrow that's just pointing in one direction. It's not a It's not an arrow like a double arrow like this. And what that's saying, what that indicates is that you're assuming, so this is happening to, it's kind of like saying that if something is insoluble, you're assuming it doesn't dissolve, but it might dissolve to a small extent. So you're assuming that this process is complete. There's no, it's not reversible. You don't have, like, this breaks up into the ions, but there aren't ions kind of going back into the solid state at the same time. Like you have the forward and reverse reaction happening at the same time. No, it's once the ions break up, they stay broken up. That's the meaning of a strong electrolyte. Okay, so let's keep reading, and then we'll go back to that beaker example. Let's see what they say a weak electrolyte is, and then we'll come back to that beaker example. So this equation says that all sodium chloride that enters the solution ends up as Na plus and Cl minus ions. Yes, assuming that you haven't, the solution isn't saturated yet, so you could, based on the solubility properties we talked about in the previous video, there could be a point where there's no more sodium chloride is going to dissolve because the solution is saturated. But if it's not saturated, then any sodium chloride that enters, you're assuming that it all dissociates 100% with no reversibility into the ions. So we call it a strong electrolyte. Table 4.1 lists examples of strong electrolytes, weak electrolytes, and non-electrolytes. Ionic compounds such as sodium chloride, potassium iodide, and calcium nitrate are strong electrolytes. It is interesting to note that the human body fluids contain many strong and weak electrolytes. So, okay, here's the strong electrolytes, and so it's saying all ionic compounds are strong electrolytes if they're soluble in water, right? This is not a strong electrolyte because it's not soluble. So you would call this a non-electrolyte. So, okay, but what you can see is you might wonder, well, how would a molecular type compound dissociate into ions? Well, okay, like HCl, right? What's going to happen is, we'll talk about this in a second, hydrogen chloride gas, you put it into water, you're going to get an H plus ion dissolved and a chloride anion dissolved, right? There's the ions. So yes, you can have molecular compounds that are electrolytes. It's not just ionic compounds, right? You would think ionic compounds are made up of ions, and so that's going to be they can break up into ions in solution, right? What else could yield ions in solution? Well, no, molecular compounds can as well. BaOH2, so you'll have, this would be barium hydroxide, starts off solid, then you put it into water, and you're going to get Ba2 plus ions dissolved, and then OH minus ions dissolved. But now we need to put a 2 here to balance it. See, there's ions in solution. All right, but now, okay, what about a weak electrolyte? We don't even know what this is yet, but here's weak electrolytes. Non-electrolytes, so again, we know the definition of a non-electrolyte is that it doesn't, there's two ways of looking at the definition. It doesn't, no matter how much of a non-electrolyte you dissolve, no matter how much, the water solution is not going to conduct electricity. Okay, so like okay, well, first of all, we can, a non-electrolyte, if you have any substance, no matter what it is, that's not soluble in water, then it's going to be a non-electrolyte, right? So that's the first criteria. Okay, but now, focusing on what we mainly want to focus on, okay, is if you have a substance that's soluble in water, what's going to make it a non-electrolyte? Well, it's going to be if it's not yielding ions in solution. Okay, so these, I think the way they're doing this is that anything they're putting in this table is soluble in water. So all of these, what's happening is they're just not breaking, they're soluble, they're just not breaking up into ions. The whole molecule dissolves, right? You have these full sucrose molecules hydrated by water. So there's no ions in the solution. All right, now what about weak electrolytes? So yeah, we talked about it a little bit. It's the reversibility. It's not a fully complete dissociation. So okay, water is a very effective solvent for ionic compounds. Although water is an electrically neutral molecule, it has a positive region, the H atoms, and a negative region, the oxygen atom. or positive and negative poles. For this reason, it is a polar solvent. Yeah, that's what makes water such a good solvent. It's those strong polar ends, those hydrogen bonds, and the oxygen end. When an ionic compound such as sodium chloride dissolves in water, the three-dimensional network of ions in the solid is destroyed. The Na plus and Cl minus ions are separated from each other and undergo hydration, the process in which an ion is surrounded by water molecules arranged in a specific manner. Yeah, so hydration doesn't just apply to ions, it's any the sugar molecules, or when sugar dissolves, are hydrated. Each Na plus ion is surrounded by a number of water molecules orienting their negative poles towards the cation. Similarly, each Cl minus chloride anion is surrounded by water molecules with their positive poles oriented towards the anion. Hydration helps to stabilize ions in solution and prevents cations from combining with anions. Yeah, that's the hydration process, the dissolving process in water. Okay, but as we talked about, though, the dissolving can happen, like oil can dissolve certain solvents that water can't dissolve. We're going to talk about more details about dissolving in chapter 12. Okay, acids and bases are also electrolytes. Some acids, including hydrochloric acid and nitric acid, are strong electrolytes. These acids are assumed to ionize completely in water. For example, when hydrogen chloride gas dissolves in water, it forms hydrated H plus and Cl minus ions. So yeah, there you go. It's not an ionic compound, but look, you have hydrogen chloride gas dissolving in water to create an aqueous solution, which kind of goes against the definition that they gave of an aqueous solution earlier. But so to me, it's just any homogeneous solution where water is the solvent is aqueous, no matter how it was created. Okay, in other words, all the dissolved HCl molecules separate into hydrated H plus and Cl minus ions. Thus, when we write HCl aqueous, it is understood that it is a solution of only H plus aqueous and Cl minus aqueous ions, and that there are no hydrated HCl molecules present. Right, it's a strong electrolyte. So now, on the other hand, certain acids, such as acetic acid, which gives vinegar its tart flavor, do not ionize completely and are weak electrolytes. We represent the ionization of acetic acid as shown here. So this is the characteristic of a weak electrolyte, this double arrow. It does dissolve, but furthermore, it does dissolve into ions. So it is an electrolyte, but it's a weak electrolyte because you have this, when the substance dissolves into ions, it's a reversible reaction. You have ions also at the same time going back to the molecular state. It's happening back and forth. But you still get these ions, right? You have the acetate ion and the hydrogen ion. We use the term ionization to describe the separation of acids and bases into ions. By writing the formula of acetic acid as CH3COOH, we indicate that the ionizable portion is in the COOH group. Yeah, so they're saying they write acetic acid this way, because why don't you just put C2H4O2, right? I mean, you could do that, but it's written this way to indicate, look, you have the CH3 and then the COOH, and so this is where the H is coming from when it dissolves in water. Okay, so now that we've got the definition of the meaning of a weak electrolyte and non-electrolyte and strong electrolyte clear, let's come back to this example here. Okay, and so again, first of all, when it comes to the non-electrolyte, you have the same molar amounts it's the same amount of water in each of these beakers, the same electric potential, and the same molar amounts, like the molecular counts of a non-electrolyte, a weak electrolyte, and a strong electrolyte. Okay, but and this is correct. The result would be you have no light, there's no circuit here. You have with the weak electrolyte, a dimly lit light, and with the strong electrolyte, a bright light. That illustration is not incorrect. But what it doesn't show, it doesn't tell the whole story. So it doesn't matter how much of a non-electrolyte you add. You could fully saturate this solution. If it's a non-electrolyte, you're not going to conduct any electricity. Yes, at a small, tiny level, there could be some dissociation into ions, but it's negligible. That's what makes it a non-electrolyte. Or it could be it's fully soluble, but it's not breaking up into ions like sugar, right, or and whatnot. Okay, now with the weak electrolyte and the strong electrolyte, yes, if for the exact same molar amounts, right, for the equivalent number of molecules dissolved, if one of the reactions is a reversible reaction and one is not reversible, or has a negligible amount of reversibility, then you're going to have, for the same molar amounts, you're going to have more ions in solution here, right? Because some of these ions they're going back to the molecular state, as opposed to here, everything's staying as ions. So that is true. But it doesn't tell the whole story, because it's not like you couldn't add more weak electrolyte here and then possibly add less strong electrolyte, and you'd have a brightly lit light bulb here and a dimly lit light bulb here. Absolutely. You could do that, right? But then furthermore, you could think about if you compared the solubility properties of these two electrolytes, what if you had a strong electrolyte that was much less soluble than a weak electrolyte? Then potentially you could fully saturate the weak electrolyte solution and fully saturate the strong electrolyte solution, and you get a more brightly lit light bulb than with the weak electrolyte, because it's more soluble. You see? So don't confuse solubility properties with electrolyte properties. It's two different properties of solutes, and we're talking about in relation to water as the solvent. They are related. Like what makes something an electrolyte and a non-electrolyte, and also strong versus weak, it is obviously related to how the substance dissolves, or if it dissolves, but it's still two distinct properties. Like we could even think about how for you could have a non-electrolyte that it's a non-electrolyte because it's insoluble. So let's think about a non-electrolyte that hypothetically, two non-electrolytes that hypothetically, if they were soluble, they would break up into ions. Okay, one hypothetically would break up into ions as a weak electrolyte. The other hypothetically would break up into ions as a strong electrolyte. But if you zoomed in at the molecular level, because in general most things aren't perfectly insoluble, right? If you zoomed in at the molecular level, for the insoluble, kind of quote unquote weak electrolyte, or you would see that reversibility happening. And for the strong electrolyte, like an insoluble ionic compound, you would see that the small amount of dissociation that does happen, it would be full. There would be no reversibility, right? So those electrolyte properties are even, you can even think about them in the case of where something is not even soluble, right? So it's two different properties, solubility and electrolytic properties. And these are, I want to be specific, these are properties of solutes. They're properties of substances that you could, like a powder or a liquid or whatever, a gas, it's a substance. But these properties are in the context of, okay, if we were to put these substances, these potential solutes into water, what's the result? That's what electrolytic and solubility properties are in reference to. Okay. The ionization of acetic acid is written with a double arrow to show that it is a reversible reaction. That is, the reaction can occur in both directions. Initially, a number of acetic acid molecules break up into the acetate ion and hydrogen ions. As time goes on, some of the acetate ions and hydrogen ions recombine into the acetic acid molecules. Eventually, a state is reached in which the acid molecules ionize as fast as the ions recombine. Such a chemical state, in which no net change can be observed, although activity is continuous on the molecular level, is called chemical equilibrium. Acetic acid, then, is a weak electrolyte because its ionization in water is incomplete. By contrast, in a hydrochloric acid solution, the H plus and Cl minus ions have no tendency to recombine and form molecular hydrogen chloride. Hydrochloric acid, we use a single arrow to represent complete ionization. Right. That's the distinguishing characteristic between a weak and strong electrolytes, that reversibility. And what they're saying here is that the idea is once you put a weak electrolyte into solution, it'll start to dissociate and whatnot, and then and then in a short period of time, in general, it'll come to equilibrium where it'll be dissociating as fast as it recombines, and you get an equilibrium concentration of ions in the solution.